Imagine standing in a world where every object seems trustworthy and solid until nature itself starts to defy common sense. Paul Dirac confronted this painful truth head-on, discovering that at the deepest level, reality refuses to follow classical rules. If electrons leave clear evidence that they exist, why do their actions defy everything we know about the material world? The answer shattered certainty and rewrote physics forever. A tennis ball sits on a table. You know it is there, solid and unmoving, until you pick it up. If you throw it against a wall, it bounces back. Nothing unexpected happens. In the world of everyday objects, actions have predictable results. If you roll a ball toward a door, it either goes through the opening or it does not. Place two doors side by side, throw hundreds of balls, and you will find two neat piles on the other side, one for each door. Each ball takes a single path, and its position can be tracked from start to finish. The logic is simple. Objects travel along definite routes, and their behavior can be explained without ambiguity. This is the foundation of classical physics, the kind of certainty that underpins engineering, sports, and daily life. The rules feel obvious. If you know where something starts and how it moves, you can predict exactly where it will end up. This is the common-sense world we trust, where outcomes match expectations and reality seems straightforward. Switch the experiment from tennis balls to electrons, and the entire picture changes. Instead of two neat piles behind the slits, a pattern of alternating bright and dark stripes appears on the screen. Each electron arrives as a single sharp impact, never split, never smeared out, yet over time the impacts build up into a series of bands. These stripes are not the result of many electrons bouncing off each other. Even when electrons are fired one at a time, separated by seconds or minutes, the same pattern slowly emerges. The effect is unmistakable. Electrons behave as if they travel through both slits at once, interfering with themselves. In classical terms, this is impossible. A particle should choose a path, pass through one slit or the other, and land accordingly. But the evidence is right there in the stripes. Nature refuses to fit into the categories of particle or wave. The experiment forces a question with no classical answer. How can something arrive in whole, indivisible hits, yet arrange itself as if it were a spread-out wave? The rules that once seemed obvious no longer apply. Fire electrons one at a time through the double-slit experiment. Each electron travels alone, separated in time so completely that no two can interact with each other. Still, the pattern of stripes appears on the detector, built slowly from isolated impacts. There is no chance for the electrons to influence each other, no hidden communication or crowd behavior. Each arrival is a single, indivisible event, a solitary dot on the screen. Yet, over hundreds or thousands of repetitions, the same interference pattern emerges, as if each electron is aware of both slits at once. No matter how slowly the experiment runs, the result never changes. The interference is robust, surviving every attempt to isolate the particles. The mystery deepens. Reality seems to follow a rule that holds for each electron by itself, not just for large groups. This is not a trick of technology or measurement. It is a feature of nature itself. When a detector watches which slit each electron passes through, the stripes vanish. The interference pattern collapses, replaced by two simple piles, one behind each slit, just as with tennis balls. The only difference is the availability of path information. It does not matter how gentle the measurement is or how perfect the equipment is. If it is possible, even in principle, to know the electron's path, the interference disappears. No adjustment to the detector restores the stripes. This is not a flaw in technology or a disturbance from observation. It is a fundamental rule. The potential to learn which path was taken erases the wave-like behavior. Nature draws a boundary. When knowledge of the path exists, the world must behave like particles, not waves. There is no loophole. The limit is physical, built into the structure of reality itself. Niels Bohr called it complementarity, the idea that certain questions about quantum systems have no single answer, only mutually exclusive possibilities. In the double-slit experiment, asking which slit an electron passed through destroys the interference pattern. If the path is knowable, the system behaves like a particle, and if not, it behaves like a wave. There is no way to see both aspects at once. Most physicists, including Bohr and Dirac, agreed that quantum mechanics does not reveal an underlying path or hidden certainty. The equations predict the chances of each outcome, but not the outcome itself. Demanding to know which slit the electron really used without measuring is like asking for a color that is both red and green. The question itself has no answer in this framework. This consensus forced a new way of thinking. Reality, at its core, is not about certainties, but about probabilities. In 1928, Paul Dirac set out to solve a problem that had stumped even the greatest physicists of his day. How do you describe electrons moving near the speed of light and still obey the rules of quantum mechanics? The existing equations either violated relativity, or they failed to preserve the probabilities that quantum theory demanded. Dirac aimed for an equation that was first order in time, matching Schrödinger's form, yet fully compatible with Einstein's special relativity. He began by examining the energy relation from relativity. Energy squared equals momentum squared times the speed of light squared, plus mass squared times the speed of light to the fourth power. Taking the square root of that relation introduced mathematical headaches. Dirac's breakthrough was to linearize the equation by replacing ordinary numbers with matrices. Matrices are arrays of numbers that do not always commute when multiplied, and that non-commutativity was essential. Dirac labeled those matrices alpha and beta. They had to satisfy special rules. When squared, they gave one, and when multiplied in pairs, their order mattered. These anti-commutation relations were new to physics. The result was a wave equation for the electron that naturally included spin, something earlier theories had to bolt on by hand. The solution was not a single number, but a four-component object called a spinor. Each component described a different possible state of the electron, including its intrinsic angular momentum, its spin. The equation also guaranteed a conserved current, ensuring the total probability always added up to 1, no matter how the electron moved or interacted with fields. Dirac's method was spare and almost austere, reflecting his belief that beauty and simplicity reveal nature's truth. What began as a search for mathematical consistency led to an equation whose implications stretched far beyond the electron. It laid the groundwork for quantum field theory and for the prediction of particles that had never been seen. In August 1932, a photograph from a cloud chamber at Caltech revealed a slender white track curving in the wrong direction. Carl Anderson, scanning cosmic ray images, measured the curvature and energy. The particle had the same mass as an electron, but the opposite charge. Here was the positron, an anti-electron, just as Dirac's equation required. The mathematics, once dismissed as an oddity, had become a map to unseen territory. Within a year, The discovery was confirmed by Occhialini and Blackett in England, who watched electron-positron pairs appear and vanish in the vapor of their own chambers. For the first time, antimatter was not just a theoretical possibility, but a fact of nature. Dirac, still in his early 30s, received the Nobel Prize in Physics in 1933, sharing the honor with Erwin Schrödinger. The Nobel Committee cited his discovery of new productive forms of atomic theory. The positron's existence settled the debates over negative energy, transforming what seemed like a mathematical flaw into a window on the universe's symmetry. Dirac's approach was guided by a belief that the laws of nature must be beautiful. He once wrote, "It is more important to have beauty in one's equations than to have them fit experiment." The Dirac equation did both. It predicted antimatter, explained electron spin, and set the stage for quantum field theory, the backbone of modern particle physics. Today, every positron in a PET scan, every experiment at CERN, and every calculation in the Standard Model owes something to Dirac's insistence that mathematical elegance is not just an aesthetic, but a guide to reality itself. Dirac's mathematics still underpins every quantum device and theory in use today. As technology grows ever more entangled with uncertainty, his insights force us to accept a world built on probability, not certainty. The deeper we look, the less reality owes us an explanation. Share your thoughts below.